We're going to talk more about Taylor series here and how we can use them to build other Taylor series for other functions, and then we'll work some more examples from our packet. So on the intersection of the intervals of convergence, Taylor series can be added, subtracted, and multiplied by constants and by powers of x. The results are, again, Taylor series. So the Taylor series for two functions, f and g, is going to be the sum of each of their Taylor series. So it's kind of weird, but you're adding, it's like another infinite sum. You're adding the two infinite series together, term by term, or however they fit together. So let's take a look at what we can do to find a Maclaurin series for 1 plus cosine 2x over 2. So what we can do is we know, hopefully, or we're trying to learn that the cosine of x, remember this cosine is an even function, so it'll start with 1, and then it's going to alternate in sign and always be even powers. So we're going to get this, and so on. So we want the Maclaurin series. So that's cosine x. So from that, we can say that the cosine of 2x is, we will replace all the x's by a 2x. So that'll be 1 minus 2x quantity squared over 2 factorial. And then we'll get a 2x to the 4th over 4 factorial, and a 2x to the 6th over 6 factorial, and on and on and on. Then we will add the 1 to that. So I'm going to slide up a little bit here. So then we're going to get 1 plus cosine 2x. Means we're just going to add 1 to that. So adding 1 will combine with the other constant. So it'll become 2 minus 2x quantity squared over 2 factorial, 2x to the 4th over 4 factorial, minus 2x to the 6th over 6 factorial, and on and on. And then we will finally divide everything by 2. And so we'll do that term by term. So the 2 divided by 2 will be 1. Now we can do this a couple of ways. We can imagine for a moment, I'm going to separate out the squaring. So that's going to be 2 squared x squared. We're going to get the extra 2 from dividing by 2 times the 2 factorial. I'm going to come clean this up in a moment. 2 to the 4th, x to the 4th, the divide by 2 and the 4 factorial. And then I guess that'll be a minus 2 to the 6th, x to the 6th. There's our divide by 2 and the 6 factorial, and on and on. So finally, what I think we can do is we can cancel a 2 with each of those powers of 2 there. So our final result is going to be that 1 minus, and then we're going to get 1 less power of 2 than we have power of x, but the factorial in the denominator will still match the degree of the power of x. So 2 to the 3rd, x to the 4th, 4 factorial, 2 to the 5th, x to the 6th, and 6 factorial. And don't forget that plus dot 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 at the end. Okay? All right, now this is a little daunting, but there are 7 Maclaurin series that should be known from memory. And when I say known from memory, I don't mean necessarily that you have to know these like you know your multiplication facts, you know that 3 times 5 is 15 and you know it that quick. But you should recognize them certainly and be able to recreate them in a matter of moments rather than many, many minutes. So you'll see these in your Taylor series packets that is on page 3 and also in our book. So I'm going to show you, kind of walk through this, what I mean by you should know them, kind of in the way that I'm going to work through these here. So we should definitely know the first one just straight from memory. This is our geometric series that is going to be just the sum of the powers of x. So we should know that quick. Then knowing that, we should be able to create this one by recognizing that we will just substitute a negative x everywhere we see the x's. And that will create our alternating geometric series, where the even powers are going to be positive and the odd powers will be negative. Then from there, we should be able to recognize that if we integrate that, we're going to create our series for natural log x. And so the integral of 1 is x, and then we're going to get x squared over 2 and x to the third over 3. This is what I mean by knowing them from memory, that you can do them this quickly. And hopefully that you will recognize the series if you see it. Then with minimal work, we can see that if we replace this 1 over 1 plus x with a 1 over 1 plus x squared and generate that, so replacing all of those x's by x squareds, and then in turn integrating that to get our tangent x as x minus x to the 3 over 3 plus x to the 5th over 5. And notice these are going to be all odd powers. And so hopefully if we encounter that, we will recognize it. So I kind of group these four together, at least in my mind, because they all come from, as a source, this 1 over 1 minus x. Then in my mind, I group the next three together. So the sine and the cosine are these alternating either odd powers with factorials or even powers with factorials. So the sine, because it's odd, we're going to start with an x because the number is an even. And so we'll go then just alternating with our odd powers over the same factorial. So this we need to know, and so on. Then we know that cosine is going to be kind of the missing terms from the sine, if you will, or they're going to alternate also, starting with 1. So now we're going to have all even powers over, and the factorials will match or agree with the powers. And then I think of e to the x as kind of the combination of those, only just as e to the x is never negative, you have no negatives here. So it's strictly addition. And now you're getting all of those terms. So no missing powers of x and their same factorial. So those you need to know from memory there. Okay, now I'm going to go to the next panel and we're going to do some problems, some of those examples, and work through our packet starting with page 2. So here we are now on page 2 of your Taylor Series packet. So we are going to use the example, the method from, it says the previous example, but what we're going to do here is try to find the different derivatives going up to the fourth derivative, and we're centered at 0. So we know that f of 0 is going to be the square root of 1, which is 1. We're going to think of that f of x. This is going to be a little bit tedious. There's going to be a lot of work here. So here's our function. So our first derivative is going to be 1/2 1 plus 2x to the negative 1/2. Then from the chain rule, that will be 2, and we'll cancel those. And so if it may be a more evaluation-friendly form, that's going to look like this. So that means f prime of 0 is going to be 1 over square root of 1, which is 1, so that also is going to be 1. So then we'll take our second derivative, so differentiating this now, so that's going to be a negative 1/2. Now we have 1 plus 2x to the negative 3/2, and again times the 2 from the chain rule, and we'll again be able to cancel those 2's. So in a more evaluation-friendly form, I think I'm still going to, well, maybe I'll call that the square root of 1 plus 2x cubed. So f double prime of 0, because 2 times 0 is still 0, we're still just getting 1 to any power in the denominator, which is 1, so that's going to be a negative 1. So remember, we're going to go until we get a fourth derivative. So now our third derivative, the negative 3/2 times a negative 3/2, I guess we're just right here. So negative times negative is a positive 3/2. We'll have 1 plus 2x to the negative 5/2 times another 2. We again get to cancel the 2's. We're going to evaluate that. I think we can probably do this okay in this form at 0, because 2 times 0 is 0, 1 to any power is 1, times 3 will be the 3. Finally, our fourth derivative, the negative 5/2 times 3/2 is going to be 15, a negative 15 fourths, 1 plus 2x to the negative 7/2 times the 2. So we'll cancel the 2, but this time we're only going to cancel 2 of that. So when we evaluate our fourth derivative at 0, 2 times 0 is 0, 1 to any power is 1, times a negative 15/2, it's going to be a negative 15/2. Okay, now we're going to try to put it together. So sometimes this is written as either a t sub 4 of x or a p sub 4 of x, either way. And so we're going to get our f of 0, which is 1, plus our first derivative, 1, times x to the first, plus our second derivative, which is negative 1, over 2 factorial times x to the second, plus our third derivative, which is 3, over 3 factorial times x to the third, plus our fourth derivative, which is negative 15/2, over 4 factorial times x to the fourth. So we can do a little bit of cleanup here. That's going to be 1 plus x. 2 factorial is 2, so we can write that as negative 1/2 maybe, x squared or x squared over 2, either way. Now remember, 3 factorial is 3 times 2 times 1, so we can cancel those. And so that's going to be a plus 1/2 x to the third. And then let's see, our 4 factorial is 4, 3, 2, 1. So I guess we can, I'm going to multiply by the reciprocal. So that's going to be 4, 3, 2, 1 over 1. We can cancel the 2's, and sadly, it's going to be about the best we can do. So we're going to have to get, I guess, if we want to multiply it out, 12 times 15 doesn't look very appealing. But I think that 10 times 15 is 150. 2 times, so we have 10 times 15 is 150. 2 times 15 is 30. So I think that's going to be a minus 180 x to the fourth. And you don't have to do all that multiplication out. You're welcome to leave it, in the factorial form as well. That's really not a big deal. Okay, let's, here we see again what we've seen before is our expression for a Taylor series. Now in example 2, we're going to do a fifth degree, usually you'd call it a Taylor polynomial centered at 0. So here we can, let's see if we can be a little more creative or clever. we know that e to the x, hopefully we know, is 1 plus x squared over 2 factorial plus x to the third over 3 factorial. Remember, we're going to go till we get to the 5th degree, x to the 4th over 4 factorial, and x to the 5th over 5 factorial. So e to the 2x means we can replace those x's by 2x's. So it will become 1 plus 2x plus the quantity 2x squared over 2 factorial, and then the quantity 2x cubed over 3 factorial, the quantity 2x to the 4th over 4 factorial, and the quantity 2x to the 5th over 5 factorial. And that would be fine just leaving it like that. If you want to clean it up, we can. I wouldn't do too much. So if you want to separate out and say 2x quantity squared is 4x squared over the 2 factorial, and 8x cubed over 3 factorial, and 16x to the 4th over 4 factorial, and 32x to the 5th over 5 factorial. I probably wouldn't do much more than that. Okay? All right, let's go on. We're going to create a 4th degree Maclaurin series. I think we've done this before, but hopefully extra practice doesn't hurt. Let's remember to be creative. So we know cosine, hopefully we know, is going to be 1 minus x squared over 2 factorial. And then we want a 4th degree, so we'll stop with the x to the 4th. We'll replace the x's by 2x's to get the quantity 2x squared over 2 factorial and the quantity 2x to the 4th over 4 factorial. You're welcome to do as much or as little of this as you like. Since there's so few terms, I would be more willing to look to try to do some more simplification. That would certainly be okay. If you want, since 2 factorial is 2, we could get to there. 4 factorial is going to be, we can cancel the 2 and the 4, which is 8 with the 16, and call that 2/3. But again, you don't have to hurt yourself. So any of those would be considered acceptable. Here we see this is off of your packet, so as you've seen in your book, I'll just point your attention there. There's an error in the original here, so I have corrected it there. I think I will try to correct it on the ones I make for you, but check and make sure that I caught that. Here's, again, we've seen this in our notes and in our book. This is our expression for the Taylor series centered at x equals a. And here we have another example. So we're going to have f of x is e to the negative x. So we're going to get the first 4 terms, and now it's centered at 1. So notice we can't use our Maclaurin series and then translate it over, because in a Maclaurin series, all the derivatives that are part of the coefficient come from the derivatives evaluated at 0. But a Taylor series evaluated at 1 has to have derivatives at 1. So that will not work. So sadly, we're going to have to say f of 1 is going to be e to the negative 1. Our f prime of x is going to be a negative e to the negative x. So f prime of 1 is negative e to the negative 1, or negative 1 over e. And then we need f double prime of x is going to be back to e to the negative x, and so f double prime at 1 will be back to 1 over e. See, I got second derivative. We want 4 terms. The first term is going to be the constant, so I have to go to the third derivative here. So f triple prime of x is going to be back to, what did I say? Negative e to the negative x. And so f triple prime at 1 will be negative 1 over e. So we want the first four terms, so we're going to say e to the negative x is going to be 1 over e, that's our f of 1, and then we're going to get plus f prime of 1, which we said is negative 1 over e, times, it'll be an x minus 1 to the first. Then we're going to get our second derivative, which is 1 over e, and we're going to divide that by 2 factorial times x minus 1 to the second. So we got 1, 2, 3 terms. We want to go 4. So now I think it's going to be a negative again. So it'll be a minus 1 over e over 3 factorial times x minus 1 to the third plus, and now we're supposed to find the general term, which means the nth term. Let me think on this a little bit. So let's do a little cleanup. We have 1 over e. It's going to be a minus 1 over e times x minus 1. That 2 factorial, so I'm going to call that a plus 1 over e times 2 factorial x minus 1 squared. And then I'm going to go minus, I'm going to call that 1 over e times 3 factorial x minus 1 to the third. Okay, so I'm thinking, and you can start it, you have the freedom to think of the first term as being the 0th term or the first term. So there will be 2 correct answers to the general term, the nth term. I'm going to think of that as being the 0th term, and this as being the first term. Then the nth term is going to be a 1 over, we're going to have an e, and the factorial is going to match the term number. So it's going to be an n factorial, and so will the power of 1 be to the n. But that's not the only correct answer. Then we're going to use the third order polynomial to approximate f of 1.1. So our third order means we're going to go to the third derivative, which will be to the third power also in this case. So we're going to evaluate at 1.1. So this is going to quickly be a, so we're going to say e to the negative 1.1 is about. This is going to become a calculator problem pretty quick, because we're going to get 1 over e minus 1 over e times 1.1 minus 1 plus 1 over e times 2 factorial, which is 2, times 1.1, minus 1 to the second minus 1 over e times 3 times 2 times 1 and 1.1 minus 1 to the third. So that's going to be 1 over e minus, that's going to be 0.1 times 1 over e, or 0.1 over e. That'll be a 0.1 squared over 2e minus 0.1 cubed over 6e. And I would go to your calculator with that. And when I did that, what did I get? I got about 0.333 to 3 decimal places. So that was like 0.332871108 and so on. Okay, now let's look at this next one. So we want to write the first 4 terms in the general term for the Taylor series for x squared times f of x. So our f of x is up here. And so our f of x, we were giving, let's see, I think we got it right here is our f of x. So if we multiply through by x squared, then, and notice that it's hard to read, but it's trying to say centered at x equals 1. So we're going to take our Taylor series and multiply through term by term. So we want 4 terms and the general term. So the first term is going to be 1 over e times x squared. See where I'm getting that? And then we're going to get minus, and then we're going to write that, I'm going to write that as x squared times x minus 1 all over e. And then we're going to get plus, and that's going to be an x squared times x minus 1 squared all over, I'm going to leave it as e times 2 factorial, because when we get to that nth term, I think that's going to be a little bit easier to try to write down in terms of a formula. So first 4 terms, 1, 2, 3, you got one more. That's going to be a 1 minus, and that's going to be an x squared times x minus 1 to the third over e times 3 factorial plus dot, dot, dot. Okay, now again, we have the freedom to think of the first term as being either 0 or 1, whichever we want. And I'd like to think of, I'm going to have the factorials match. I want to think of the factorials and the powers as matching the term number. So I'd like that to be 2, 1. So I'm going to think of it as starting with 0. So that's going to make our nth term, the way I'm thinking of it anyway, as x squared times x minus 1 to the n all over e times n factorial. And don't forget to add your plus dot, dot, dot. Oh, and I need to alternate the sign. So I forgot that. So this was a positive, then a negative. So we can get the alternating sign by going -1 either to the n or to the n plus 1, whichever is going to match. So I would start with n and say, okay, if I plug in 0 for n, is that going to give me the correct sign there? And -1 to the 0 is like anything else to the 0 is +1, and so that's going to be what I want. And so I'm going to tack that term on either in the beginning or the end. I think I'm going to squeeze it at the end, and so that is going to be part of our nth term to get the alternating sign. Okay, oh, we got another really tough one here. So let's slide down. This is a really hard one. This is actually a free response question from an AP exam, an earlier AP exam. And this didn't show through very good just in the copy, but that's supposed to be a 4 factorial. So here's our Maclaurin series for some unknown function f of x. 1 plus x over 2 factorial plus x squared over 3 factorial plus x to the third over 4 factorial plus dot, 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 plus here's our general term x to the n over n plus 1 factorial. Now, we want to find f prime of 0 and the 10th derivative at 0. So here is the efficient way of thinking of this. We want to know that any Maclaurin series is going to be of the form f of 0 plus f prime, I'm going to write that down below. It's going to be f prime of 0 times x plus f prime of 0, f double prime of 0 over 2 factorial times x squared out to the nth derivative at 0 over n factorial times x to the nth. Now, looking at that, we know that f prime of 0 is part of the coefficient of x to the first. So when we look at our Maclaurin series, we can see that the coefficient of x is 1 over 2 factorial. That is, 2 factorial is 2, so that coefficient of x is 1/2. And we can see from what we know about our formula for Maclaurin series that the coefficient of x is f prime of 0. Does that make sense? So without doing a ton of work, we can see that f prime of 0 must be 1/2. And we have figured that part out. Now, the same thing is true for finding this. We know that our formula matches the order of the derivative with the degree of the power of x and that same factorial. So we look first for the 10th degree. So if this is our general term, then when this n is 10, we're going to have x to the 10 over, and that's going to be 11 factorial. Now that we know from our general term from any Maclaurin series has to be the 10th derivative at 0 over 10 factorial. So that allows us to set these, now the coefficient here is a 1 over 11 factorial. So we can say, you with me here, 1 over 11 factorial, that's the coefficient according to our formula, must be the 10th derivative at 0, which is what we're trying to find, over 10 factorial, because that's what we know about that coefficient of x to the 10th in a Maclaurin series. So we can solve now for our 10th derivative by multiplying both sides of that equal sign by 10 factorial. So now with what we know about factorials is 11 factorial is 11 times 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1, or 11 times 10 factorial is going to now be our, no, I didn't write that very good, is going to be our 10th derivative evaluated at 0. And so once we cancel that, we can say conclusively and as painlessly as possible that our 10th derivative evaluated at 0 is actually 1/11th. Kind of crazy. Okay, now they're saying let's find out what is x times f of x. So remember, here is our f of x up here. So we're going to multiply that by x. So our g of x, if we multiply through term by term, that's going to be x. Then that's going to become x squared over 2 factorial plus x cubed over 3 factorial. That'll be x to the 4th over 4 factorial. When we go out to that nth term, that's going to become x to the n plus 1 over n plus 1 factorial, and on and on and on. So I overachieved because we really only needed the first 3 terms, and I have 1, 2, 3, 4, and this is a general term. Does that make sense? Now here's one way that they sometimes will make you have to know these Maclaurin series from memory. So the hope is when you look at that and squint at it a little bit, you'll say, man, that looks an awful lot like e to the x, because e to the x is 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial, and on and on and on. So our function g of x is the same as e to the x, except it doesn't have that 1. And so we can then say g of x is e to the x minus 1. See how that works? Okay, and that takes us to the end of this one.